Hello students, this is a compensatory online lecture due to the physical mode, since the physical mode class was not able to take place yesterday. So I will compensate it with an online video. So the topic of this lecture is unique properties of nanomaterials. And we will be learning about the defects that arise in nanomaterials, then the grain size, which I have given a little bit of introduction in our previous class, so the grain size is important, then the different physical properties like magnetic, electrical, mechanical, optical properties, how they are related to this grain size, and then we will discuss about the grain growth behavior under the conditions in which this grain grows. Now we'll start with our discussion with the defects that are taking place. So when we say defects, we mean that there has been a perfect order of atoms arranged in the form of crystals which has been distorted by some means. This is what a defect means, distortion of a perfect order of atoms. Now to understand the defect, you need to understand that looking a metal under the microscope or any object under the microscope, we will first look at the grains. So these are the different grains. By grains, we mean that regions where there is a particular crystallographic orientation existing. That means atoms are arranged in a certain fashion. And what separates one grain from the other is the way the atoms have been arranged. And the interface between these two grains, any two grains, is called the grain boundary. Right. Now, whenever in a perfect set of atoms, there cannot be any material without any defect, and these defects again can be classified into different types based upon the material in which we are concentrating. So let's say defect types. One of the defect types I have already discussed in my previous class is called dislocation. That is actually the defect which is responsible for any plastic deformation taking place. Dislocation, and there is a vector associated with this dislocation that is called the Burgess vector. B given by the symbol B. So apart from these defects, there are other defects like there can be an interstitial atom. They are called interstitials. Then there can be a substitutional defect. Substitutions. The difference between two is, suppose you have a perfect set of atoms arranged in this fashion. Let's say these are all atom E. Suddenly, there is a small atom that goes and sits in between these atoms. So this is then called an atom B, and it is called an interstitial. Or it can even so happen that one of the A atoms gets replaced by this B atom. Now for an interstitial, this B atom, size of this B atom should be much less than the size of the A atom. However, for the substitution, the size of B should be close to the size of A, if not equal. Now, based upon these defects, the whole alloy system is based. Like when we talk about the different alloys, sorry, okay, when we are talking about alloys, it basically it means that you have a base metal, and it has some of the base atoms, or it has been incorporated some very small amount of other metal. Let's say the base metal is A, and very small amount of the metal, as we have seen in the defect, is B. Now B can go inside A in two different ways, as we have seen, the substitution and interstitial. So alloys also can be of two types. One is called the substitution alloy, and one is called the interstitial alloy. However, when we say alloy, we mean that it's the substitution alloy, unless and until it has been particularly told that we are dealing with the interstitial alloy. Now, a very good example of an alloy is your stainless steel. Stainless steel is an alloy where the base metal is iron, and it has been alloyed with carbon plus some other elements like chromium, manganese, etc. to give its different texture and different properties. So this is the substitution and interstitial alloy. Now these defects that we have discussed, they are basically they are mainly occurring in the case of metals. By metals, we mean that there is only one type of atom dominant. So the metallic bond is basically ionic ions of certain metal on whose metal we are talking about, and there is an electron C. So its ion cores in a C of electrons. This is what defines the metallic bond. Okay, so basically one element is dominant. However, in the case of ceramics or non-metals, there is always at least two different types of elements involved. So in the case of ceramics, there is always a positive ion that is called a cation. It's positive in nature, and there is an anion. And the bonding that exists between these two, the bondings is a combination of, this one, cation is positive, then we have anion, which is negative. And the bonding that is existing between a cation and anion is a combination of ionic and covalent. Okay. Ionic bond is the bond that is taking place in NaCl, where we have Na plus and Cl minus. There is Coulomb interaction between these two oppositely charged ions. And covalent bond, of course, is a bond which is formed by sharing of electrons. Like in the case of ethane CH4, we have 4 electrons and you have hydrogen with 1 electron. So these atoms, 2 electrons are shared. So if there is 4 electron at the outermost shell of the carbon atom, it requires another 4, so that is compensated by 4 hydrogen atoms having 1 electron each. So this is your covalent bond. Now, in the case of metals, if you look into the metals, the defects also will be different. The defects will mainly, there will be also an absence of atom as or interstitial, as we have seen in the case of metals. Those will be in such a way that the charge neutrality is maintained. Right. For example, in absence of a positive ion, A plus, if somehow A plus is missing, so it will be accompanied by a similar anion missing. Right. Like now we have A plus and B minus arranged in a fashion like this. So earlier in the case of metals, it was only one single type of atom, there was no charge. But in the case of ceramics, we have positive ions and negative ions arranged symmetrically. Let's say in this fashion. A plus, B minus, A plus and B minus. So here somehow this B atom is absent from this structure. So if this cannot happen all alone, if this B atom is not present, it must be accompanied by an absence of an A atom, so that the charge neutrality is maintained. Similarly, if there is an interstitial of some different atom, say sitting inside this place, so there will be an oppositely absence of an positive ion vacancy. Suppose a negative ion goes and sits, say some more other negative ion, let's say C minus. C minus somehow goes and sits in this place, so it will be compensated by a vacancy of a positive ion. Okay. So the basic idea is the charge neutrality should be maintained. It should be charge neutrality should be there. Okay. Now we have got different names to the different types of defects that I've told you. If a positive as well as, let's say NaCl, let's say take another example. Let's say we have NaCl. Let's say Na plus and Cl minus. This is the structure. So if there is an absence of Na, there will be an absence of Pa. This defect, you have two different absences. This is called a Schottky defect. And if the defect is such that an ion is going and sitting at the interstitial positions, and which is causing a vacancy of the ion of opposite charge, then that defect is called a Frankel defect. So there are two defects. One is Frankel, one is Schottky. Both of them are based upon maintaining the charge neutrality. Okay. So let's recapitulate what are the defects that we have studied till now. We have studied about grain boundary. In fact, grain boundary is also a defect. We have studied about grains. We have seen that if this is the average grain diameter D, we have seen that how the decrease in D will cause the yield stress to improve because of this relation sigma y is equal to sigma 0 plus ky D, right? And then we have studied about distributions. Now today we have studied about interstitials and substitutions. Then we have studied about Frankel defect and Schottky defect. See, they are prevalent in the case of ceramics, whereas all these other defects, including dislocation, they are more prevalent in the case of metals. So apart from these and metals, there is one more type of defect which is called formation of twins. Twins are nothing but mirror image. So if you have a grain boundary region, if the atoms are so arranged that one grain, if you compare two grains, the atomic arrangement is just the mirror image of the adjacent grain, then so it's mirror image, atomic arrangement. Then we call this one as a twin. Now twins are arising in the case of, mainly in the case of metals, by a process called severe plastic deformation. Severe plastic deformation is a method of making the grains go smaller in size. The way it is done is we deform the material SPD through a process. There can be different ways by which we can apply SPD. One of them is equal channel angular pressing. So we have a metal, we have a die in which the metal is fed and it is pushed with a plunger. So the metal comes out having a uniform cross-sectional area. It's also called extrusion. So in this case, now naturally the metal that we are dealing with here, this is the metal, say, this metal here, this is under severe pressure. So that is why this severe plastic deformation is there. Now due to this severe plastic deformation, what is happening? New dislocations are being created inside the grains. Initially there were some defects, inherent defects. Now due to SPD, new dislocations are being created. So the picture looks something like this. This is a grain. These were the grains. So we had initially some dislocations, pre-existing dislocations, which normally occurs in different grains, already existing. Now this has undergone a severe plastic deformation. Plastic deformation means that new grains have been created, and the grain creation is such that there is pile up of grains at the grain boundaries. Grains start to pile up at the grain boundaries, and the energy is so high that it leads to the refinement of the grains. Refinement of the grains literally means the grain forms into subgrains. One grain divides into more than one grains, they are called subgrains. And by going to subgrains, the thing that is achieved is that the dislocation density, the dislocation pile up at the grain boundaries is somehow reduced to some extent. So Severe plastic deformation is another way of making the grain size D go down. Okay. Now, once a material has been reduced in grain sizes, then we call it as UFG material. UFG material is ultra fine grain material. Ultra fine grain material, UFG. When you have achieved UFG, and so say the refinement has been such that it has gone into nanometric order. Now 21 minus 9 meters of this range is the small crystallites that are formed. So it is nearing amorphous. So at this point of time, we would like to regrow the grain. So what we will do, we will heat it, apply some sort of heat, so that heat will again cause the grain growth, and this process is known as recrystallization. And this process, the recrystallization is a process that occurs, and the application of heat to cause this is known as annealing. It will not only it will increase the grain growth. Prior to that, it will reduce the residual stress that was developed into the material due to excessive mechanical force applied in SPT. Okay, so I will continue this in my next lecture.